Right, it has been 2 minutes, so we're gonna start now. Good afternoon, everyone. Thank you for joining today's webinar. My name is Chakung Na from Rutgers University. On behalf of the Principal Investigator of Bridge Research Program, Hani Nassif, I'd like to thank you for participating in this webinar series. And this webinar is sponsored by NJDOT Bridge Research Program and hosted and organized by Rutgers RIME Group and C2 Smart Center at NIU. And BRP is the consortium among Rutgers University, HNTB, Rowan University, and NIU. And our team provides technical support to NJDOT in several areas, including innovative materials and technologies that Dr. Mantawy will present today, and bridge design manual updates, material and construction specification updates, guide plates, and standard drawing plates updates with HNTB and forensic engineering support. Today's webinar's title is Additive Manufacturing Techniques in Infrastructure Applications, and our presenter is Professor Islam Mantawy from Rowan University. Professor Mantawy is an assistant professor in Civil and Department of Civil and Environment Engineering at Rowan University. His research focuses on structure and bridge engineering with emphasis on additive and robotic construction, accelerated construction and repair, structure health prediction, hazard resistant infrastructure, and net zero construction technologies. At Rowan University, he leads the Additive and Robotics Construction Laboratory, where his team develops advanced methods for 3D printing concrete and metallic structure to improve construction efficiency, sustainability, and structural resilience. He received a Best Research Paper from Institute of Structural Engineers in 2020, and prior to joining Rowan University, he served as a research assistant professor at Florida International University. We are pleased to have him with us today to share his expertise on this important and emerging topics. And Professor Mantawy, thank you for joining, and I'll now turn it over to you.
Thank you, Jacob. Welcome, everyone. I hope you hear me well. So today I'm going to talk about additive manufacturing technique in general and how are the work going on in different aspects at Rowan University here and trying to validate new concepts and hopefully pathway for scale ups. And we will have a discussion later on with audience on different infrastructure applications suited for those technologies. So basically, I'm going to start with introduction and overview, background of what is concrete additive manufacturing and metal additive manufacturing. Moving to a topic that introduce our lab and capability. I kind of picked three projects from our ongoing projects at Rowan University. One related to flexure beams, second related to bridge columns, and third one related to 3D printing of concrete underwater. And we'll end the presentation with open discussion on what could be application for infrastructure at large. So starting with introduction and overview, this slide I use it everywhere I go to show that how the casting or concrete construction been evolved over years. The one on the left side is from 1950. The right side is from 21st century. So basically we are still using same mindset of constructing elements using formwork reinforcement, the way we have the reinforcement and vibration and flowable concrete. A little bit in the operation or equipment development, but the same spirit of the construction is the same formworking. That also could be translated to the same way we have our steel fabricated or steel making process technique related to 1950s and 21st century, the way that we produce our steel. This presentation will not focus on 3D printing of steel, which is a integral part of our lab, but basically concrete side, and maybe in future venues we will have a presentation for the steel side too. So looking to additive manufacturing in infrastructure or construction, ISO have different designations or processes for additive manufacturing. The main concept is building structure layer using layer on a layer or top of a layer. So we have sheet lamination, material extrusion, binder jetting, material jetting, powder bed fusion, vat photopolymerization, and direct energy deposition. In infrastructure application, a material as concrete extrusion can be used, and also binder jet for concrete and metals, and all the powder bed fusion and direct energy deposition also candidate for infrastructure and building application. The one I have more of blue text here is where Rowan and my team is focusing on right now, is with material extrusion and direct metal laser centric for metals. So basically, why we are doing advanced manufacturing or additive manufacturing, and a lot of advantages like reduction of labor, reduction in labor needs, enhanced labor skill set, also time saving, reduction of material wastage through optimization, and also broaden the design creativity and problem solvability. From carbon footprint, you also could optimize structure and protect the existing structure, so you reduce the carbon footprint over the life cycle of the structure. It introduced something really interesting called on-demand manufacturing. I mean that you print when it's needed, so that it reduced the stocking and supply chain risks, and also provide competitive edge for US and in terms of economy and businesses. So back to concrete 3D printing, we classify here at Rowan concrete structure now into 3 categories. The first one is conventional, where you have forming, reinforcement placement, and casting. Most of the existing 3D printing techniques actually is what we call hybrid construction, because instead of having formwork, we actually printing majority of the structure, or printing formwork, placing reinforcement, and have after printing processes of casting. At our lab here at Rowan Arc Lab, we focus on optimization and ways to actually finish the structure as you finish the process. So inline reinforcement, and also design and compression all these structures. So basically, to give a background here, historically concrete is made to be a flowable material with a sufficient slab to fill formwork and encapsulate reinforcement. However, in 3D printing technique, we are changing the material rheology and altering it to be able to build a layer upon layer, which actually basically introduce a brand new material in a sense. So you have a lot of challenges. One challenge is actually is related to the when you build up. So you actually have an active structure or dynamic structure that evolve as you print. Opposite to the formwork, when you fill it up, you also have the entire structure in a way or another exposed to the environment, not the same as a formwork. So you could have early age problem like shrinkage and cracking. You also have challenging reinforcement techniques as you print. Researchers now try to solve that, and our lab is leading that effort too. And lastly is as you print layer by layer, you always introduce anisotropy to the materials, so the properties are not always the same in the 3 different directions. So just to tie it to a different, I'm not sure if in videos you can see it or not, but hopefully you see it through the presentation. So here is another process of metal additive manufacturing, with WAM, was basically welding on demand, building structure, and instead of hot rolled or cold rolling. So basically, in the body of the literature for the metal side, you will see this technology is being used in different scales. One is a smaller scale to verify material. Second is mid-scale, where you can use it to actually reinforce existing steel structure and enhance buckling behavior. And the largest scale that was used in Amsterdam, where the bridge is printed fully, as you can see from the right side. At Rowan, we use direct metal laser sintering, which is a different process that involves distributing particles and using laser beam to selectively solidify material. And this process actually introduced a lot of variation in material properties and the printing speed, et cetera, et cetera. So since we are not covering metal today, I will jump to what our lab is focusing on. As I mentioned, we have a group of students, one myself. We have PhD students working in 3D print of concrete. One who's working in metal side, and we have graduated Zaid Hanoun. I think he's actually one of the audience today. I think he's having a homesick from Rowan and just maybe try to come back. So we have two research area. One is concrete additive construction, other one is metal. In the concrete side, we focus on optimization, how we create it for hazard system, how to create material that is low in embodied carbon and also using local source materials to reduce the carbon footprint, how to integrate new reinforcement techniques and multifunctional structure. We have very similar interest in the metal side, but as I mentioned, for sake of this presentation, I'll skip the metal side. So basically, our lab developed our own material, locally sourced from New Jersey. We barely use commercial material. We were able to use within 20 miles of Rowan the raw material and engineer our own printing system from materials to testing. So we are actually using a lot of more processing and testing from flow table to setting time to testing through the system as performance-based testing for extrudibility and buildability and how the layer is fused and actually destructive testing for compressive strength and non-contact sensing using LiDAR scan. For some reason, the videos are not running, and I'm not sure what's going on with my laptop. I wish actually the videos are all over the slides. So I'll try to see for next slide. Otherwise, I'm gonna maybe stop sharing and resharing. So the presentation. So the printer we have here at Rowan is 20 feet long. Can enable printing 20 feet long by 4 feet by 7 feet high. We can print from 1 inch per second to 4 inch per second, and it can continuously rotate around itself 360 degree. And you can see here two different systems. One is the pumping system that we have using agar to regulate the extrusion, and other system that use a smaller syringe tube. Yes, let me re-share my screen. Sorry for this.
Yeah, in the meantime, anybody has a question, please, there's a Q&A button at the bottom of the screen that you can ask question by chatting, or you can raise your hand, then I will let you speak up at the end of the presentation. Thank you.
Let me close my slide and open it.
Did you reshare it? I don't see it
Yeah,
yet.
I'm gonna be resharing in a second. So
Sure.
okay. Let me share now. Do you see my screen?
It's coming up. Yes, it's up now.
Okay. So
The video does work still.
I don't know if he's still seeing.
Okay, I think it works now.
Okay, sounds good. So the video is hopefully working here. This is a printer that we have in place, and I just explained the capability of it, and I will show you later on the more capability that we're going to be adding soon. So the system we have can print really small scale up to like 8 millimeter nozzle in the left side using a syringe tube, and can scale up to 1.5 inch layer thickness. And as you can see here in the middle one, we're using an auger system, and the right side, we're using direct pumping from the pump to the nozzle. The same material being printed from a tube to an auger to the printing system, and I can see the quality of the print here. We also have mixes that we formulated using fibers. So the mixes include steel fibers. We examined 4.5 millimeter, 6 millimeter, and 12 millimeter, 12.7 millimeter within the mix and extruded within the matrix. So you can see here, we also have various mixes that actually printable with steel fibers. We also did a lot of work where we try to examine the slope stability. This material does not use any accelerator, so it rely on exothermic reaction and heat of hydration that kicks later on and continuous curing. The material showed really extraordinary application with different slopes, as you can see here. This is a moderate slope of 26 degrees from vertical position, enabling us to print various designs for pyramids. And this one was also with steel fibers. We also trying to examine printing an even more steep slope. So with and without fibers, we were able to achieve 45 degrees stability from vertical position for mixes without fiber. This number increased to 65 to 70 degree from vertical position, which is very steep slope. As I mentioned, we are not using any accelerant in our mixes. So our mix called one component. Whatever you mix, you pump, you get at the nozzle. However, there's other systems that use injection of accelerant that accelerate the setting immediately at the nozzles level, which is called 2K, which we are not using. We have capability, but most of our research is done with 1K. So this is also another video that we actually do stress testing, meaning that we print until it fails and to understand what exactly slope could be safe for printing. And as you can see here, it starts to deform from the left side and almost printing in air, and some added load from the cantilever left side that led to a partial collapsing, but this helped us identify what could be safe printing slope. We also work on geopolymer material, which basically is cementless concrete that use byproducts and chemical activators to achieve the same binding behavior as conventional concrete. I have in my third project I'm going to be presenting today, I'll have more information to share. So this is end of introduction and what our team at ARC Lab working on in the general perspective, but here I'm selecting 3 different projects that we are working on right now, try to enable this technology to structure application. So basically, we have application for flexure beams, so how we can optimize those beams and how we can incorporate reinforcement, given that concrete alone cannot be a flexural member without reinforcement and an ability to add reinforcement as we print. So we actually working a lot in optimization, especially structural and topology optimization, which is a technique that actually use algorithm and models to optimize material layout within user-defined space with set of rules like load, condition, and constraint to maximize performance with using less material. So you can see here from ANSYS software that showed you the process in the metal side, where you can see the left side cantilever actually can be optimized to use much less material and have the same performance, even better than the original one. So the process is not invented by us. It's in literature for years, and people are using it to optimize, different structure. Here's a work at Ghent University in Belgium, where they actually 3D printed a shorter bridge, and it was segmentally printed and connected together using post-tensioning. So just to give a background of how important the reinforcement is needed for those structures, especially flexion member, not compression-only structures. Here is a simple design of a beam that include tension reinforcement and compression reinforcement to hold the stirrups, and the stirrups to carry the shear reinforcement distributed over the length with different spacing. And This is actually was governed only by the way we have the formwork. So the formwork actually governed the way we have reinforcement. And since we don't have formwork anymore in 3D printing concrete, the mindset has to be changed in how we reinforce our structures. So basically, the first concept is what's called bio-inspired design. So basically, we try to see how honeycomb actually build up their hives and honeycombs. So basically, we'll try to integrate the same concept where we'll be able to 3D print the beam, not upside down in the side, not in the vertical position. Print those hexagonal cells that mimic the honeycomb, and actually those cells can allow us later to selectively fill those smaller cells immediately after printing, and where we place our reinforcement too. So you can see here the trajectory of tension line and compression lines, and the red cables here is actually matching the tension lines and allowing us to fill as needed the compression line and the tension line to provide composite action with the beam and leave opening where the stress are almost zero or small, very low. So basically, the process will include printing those hexagonal beam, student now placing reinforcement, but in future, those reinforcement can be integrated with a robotic system. So basically, you place the reinforcement exactly the same topology of the tension line and printing on top of it as an inline process. The video is going and the student continue printing and placing reinforcement as is needed. The cable design is really interesting because actually it bend in a way that also allow it to arrest shear cracks. So we basically are optimizing the cable also on this reinforcement techniques here. So as layer by layer, you can see printing one layer, next layer, third layer, and after that placing reinforcement. Printing on top of it, completing the structure also allow us to print with rigid rebar. I'm going to show later on. So basically what you can do is you can create these layers and embed those reinforcement. And at the end of the printing, you end up having the same printer changing the rheology of the material to be flowable and selectively fill the cells immediately after printing, not waiting. So basically you can see compare the color of the concrete between the cast and the print is very similar. This is very critical because allow the two material to have the same range of hydration and fuse them really nicely here. So this end up having a 3 feet long by 9-inch deep, 3-inch wide beam that we printed with different techniques, including cable reinforcement and some rigid reinforcement we call like regular rigid reinforcement. So basically those was one of those beams or few beams actually were tested at Lehigh University, and we did a lot of digital image correlation testing on those beams. And you can see here, because the cable we use is kind of flexible, so when it cracks, actually it takes time to re-engage. It's not fully bonded as a way that rigid reinforcement are bonded. So we usually have drops in the capacity, but always keep going up until yielding the strand itself. And here is one example of the test that we did at Lehigh University, where we did digital image correlation on those beams. So you can see here, crack started almost near the middle, as any regular concrete structure. We notice that cracks are wider here because of flexible cable that we use. So we moved to rigid reinforcement in different iteration in future, where if we work that we did and the future work we're gonna plan to do. So you can see here the crack are initiating as you load the structure, and the cable are more engaging in carrying the tension force. We didn't notice any shear cracks, which actually verifies for us that the cable layout was sufficient to arrest the crack at the shear zones. Can have the video running for a few minutes, but for sake of time, I'll move to more testing that we did where we used the U-bar shape, so bend bar with the U shape. And in this particular beam, we used a very weak actual mesh wire, like chicken wire mesh wire that is around the opening here to try to stiffening it, but we don't have any shear reinforcement at the end. And the goal here was first to understand the material, the beam and the material's capacity and shear. And you can see here the left side of the slide, very nice, well-known shear reinforcement, a shear crack that formed, and the beauty of it formed within the cast and also around the printed element and the cast element. So basically, it allows us to understand the slopes and angles, and also how to design this for future work, which what we did in future work, where we used another type of rigid welded wire mesh to place it during the prints. And here is example of welded wire mesh that we used against a template. And here you can see that we were able to completely eliminate the shear cracks and activate flexure behavior, and we're able to get those behavior. And also we continue and also using different type of shear reinforcement, not rigid mesh wire, but also bend bar in terms of zigzag shapes, and we also continue testing that. So our plan is to producing more of those beam after verifying the shear capacity, flexure capacity, and tested them with digital image correlation to document the behavior and see how we can scale this application up. The second project, which I selected today, is related to how we can use this for a seismic application for bridge columns. I know New Jersey is not a seismic zone. However, this is needed for West Coast and other states that active in seismic. So basically, the resilience diagram here is showing that over time and functionality, you need to really minimize this diagram or this indicator, because the more time you need for repair and the lesser capacity of the structure could lead to downtime, longer downtime. So basically, you are aiming to reduce the repair time and also reduce the damage to the structure. So based on my PhD topic at University of Nevada, Reno, we developed rocking columns for bridges. Basically, the idea is to use pre-tension or pre-stressing strand in the middle, use regular rebar to dissipate energy. The way the moment rotation curves will develop, as you can see here, is after you add them up, you can get the flag shape that self-center the structure back. So we did test that bridge in 2014, and as you can see here, significant deformation, but after end of the earthquakes, everything aligned very nicely to the vertical position. As you can see here, significant deformation during earthquake, but since we are using a pre-tension or pre-stressed strand within the column, it allows us to self-center the column after earthquake, even during the earthquake also. So what we noticed from a damage perspective, that we noticed almost no cracks to concrete, which looks good, looks amazing, and the inspector goes and see no damage. But the main problem was the damage within the column in the rebar, that is dissipated energy yielding and fracture, and also some bulging that happened to the tube. So we thought about, can we work on a project where 3D printing can produce a better system? So we spent time understanding how rocket system work, how damper is developed in the structure, and also how seismic isolation can be integrated in a sense. We also talk about how we can also use our human body and other creature bodies to understand joints and how they connect as a ball socket connections and ligaments. Here is for hip joints and shoulder joints. So that actually inspired us to move the energy dissipation devices to be external, create flaring system at the end of the column that allow us to move from a cylinder to a flare with different slopes that engage as we rock. So I'm going to explain that in a slide by slide here. So basically, you need to eliminate damage to the foundation because it's a capacity protected system. So basically what we did, we created this column, which is 3D printed and post-tensioned later with the foundation. During the rocking motion, the structure always tip in 4 points because of a cylinder design. So that imposes tremendous amount of stresses on the foundation and the vent cap. And we change that design using 3D printing and ability to print layered element with different concave shapes that enable us to create surface as a trough rather than a concentrated point, which actually what we have in our body too. Ability to dissipate energy instead of permanent damage of rebar inside that warrant total replacement. We supplemented the energy dissipation using either external elements with rotational capability or packing the gap between the curvatures here with damping materials like polyurethane or other engineered foam. So that is actually similar to what we have for our articular cartilage in our joints. And as I mentioned early on, I was ahead of myself using external elements that use friction instead of yielding that enable us to activate rocking early on. So we did testing on those elements to verify the dissipate energy as the rocking happened. And we went and we are in process of actually the summer to test those columns under rocking. As if you notice, we don't have any reinforcement in the column. The idea here is we make the structure more flexible. You shift the period of the structure so the demand is much less. However, it's too dangerous and too difficult for engineers to accept no reinforcement, so that we start asking ourselves questions that a few slides will answer how we're going to reinforce those columns. So here is basically how 3D printing can allow us with form free to build those columns and creating this concave structure. So here is just printing the printing process from initial printing to midway to at the end of the print. This is difficult to do with creating this ball connection, if you can see using formwork. So basically, our material is capable of creating this nice stable shapes. And as you can see in the middle, we are leaving cavity to post tensioning. So basically, this is what I'm telling you about testing in future. We printed different designs that we're going to be testing very soon. So this is the big question, really. No reinforcement, no one will accept that. So we went back to see how conventional columns in building and bridges are designed. Usually you have circular or rectangular columns, and you have spirals and for confinement and shear resistance, and you also have a vertical vertical rebars. In post tension configuration, you will have opening in the middle or duct to accept the post tension. So basically, what we thought about it is actually to 3D print the majority of the column, leaving cavity for rebar placement or cavity for post tensioning. And you can see here a mock-up print that we printed for the 2 feet long, 2 feet diameter column, where majority of the column is printed and rebar cavities are left. We're going to show the process one by one. Here is a scaled column that is 6-inch in diameter. Majority of the column is being printed and cavity is left for post tensioning and grouting the material, grouting the cavity for longitudinal reinforcement. So basically, here is the process of printing. As I mentioned, in a larger scale, those print material be like the dominant material in the column. You also can place reinforcement and fill it using the printer itself by changing the rheology of the material. You can do it early on, but you need to place the material the reinforcement first and cast or fill it later, right after printing. But for just safety for ourselves, we just actually fill it a few days after to allow the column to be cured. We incorporated in vertical reinforcement, however, we didn't have spirals or ties, so we actually went and studied different materials in literature, and we found out that polyurethane material that have really good and very excellent like water resistance and impact resistant capability can be actually sprayed against the column and provide significant confinement that is similar or close to what spiral will add. So basically, we're trying to broaden the application of materials that could fit a specific application or reinventing reinforcement in a sense. So what we is a process, you print, you place reinforcement and robotic casting. You do the spray for the confinement as external confinement, and this can be a robotic system or production line with robotic and minimum human intervention. We actually did the test for different columns, two iteration per every group. So one is printed only, one printed with rebar and cast, one is printed and sprayed with Broria, and one that has all, which what we desire to. So we did also test that at Rowan University under compression machine, as you have a 600 kilonewton compression machine that we are using. And here I'm showing the different failure modes that we receive, from brittle failure for no reinforcement, just a shell, to also brittle failure, but with rebar inside, and also on the list is using the Bulgaria material. As a comparison, we noticed that with a material that the column that has the confinement showed more of a ductile behavior after reaching the maximum, if compared to the one that has no spray. And also we have don't have the slide, but also you can see the increase in compressive capacity. So this column was 6-inch diameter and carried around 250,000 pounds before experiencing any damages. The third project is the project that is really related to 3D printed concrete underwater. It's a very emerging technology within an emerging technology of 3D printing. So people try to see, okay, can we, and we do have casting concrete underwater, can we actually print underwater? And there's a lot of challenges that we find in literature. As a chronological order here from Rowan, we actually think we are one of the first people that printed underwater. That happened in November 2023, which we're trying to see if we can print underwater where water can be a media for supporting slopes to go to a severe slope as we print. So we print a structure underwater and off water. We also, later on, we try to print for different funding competition, different structure. However, since then, we found that it's going to be very good topic for research, where we can try to print with concrete underwater, and I will show later what could be the benefit of this. So we also, as I mentioned, work on geopolymer concrete that use byproduct and activator instead of cement. We came up with really different designs for mixes that can be printable. As you can see here, for the mixed design, we did two phases. One is called in-air printing. We published paper on it, and we have papers now under review for phase 2, which we did for underwater. So basically, the same process that we use for printing is with different material, but this material really sits fast. It's still 1K, but the chemical activator actually enable fast chemical reaction and solidification. So basically, we went through a smaller print from hexagonal to cylinder to sloped. The material doesn't have a really great slope stability compared to what we develop in cementitious material. However, we still were able to achieve some slopes. Here is an example of a smaller print. Material open time, which is the time available for you to print, is very short compared to our cementitious material. So we need to really conduct the process very fast. We also were able to demonstrate that the material can be printed also underwater. So as you can see here, we have our own water tank and fill with tap water and use the material and print underwater, which is a little bit challenging. And I think we reach out to really less wash out compared to other material in the markets. So basically, as you can see here, another demonstration was flared structures and ability for the structure to withstand underwater. And as you can see in the midway, we have some hiccups in the process of printing, but was able to continuously print even with some deficiencies. We also thought about how we can impact the water by leaching the materials, especially the ions, during the print. So we did some water assessment, water quality assessment to measure turbidity and pH monitoring, especially this material is alkaline based. So basically, we did a lot of work. I don't know if it's not going to be a focus of this presentation, but this shows that impact of fresh printing of concrete underwater, especially geopolymer, on turbidity, which is basically the particle suspension and release, and the pH value of the water you print with. Still ongoing and nothing really scalable to implementation, but it's emerging technology within emerging technology, as I mentioned. A compressive strength, you can clearly see that it's in air, it's more and higher compared to underwater. And we also, this material can also perform better with thermal treatment. So adding, placing it in furnace or heating up the water around it. So our next goal now is to go to continue working this topic and also develop cement-based mixes to broaden the application. That said, we will have maybe 5 minutes discussion. I have a few slides to open the discussion for the audience and how we can use this technology for infrastructure application. Basically, the work we did in the hexagonal beams and bio-inspired beams with reinforcement can enable us later on to scale up to bridge girder and bent cap. A lot of work need to be done, a lot of work with collaboration with PCI and pre-stressed fabricators, how to introduce pre-stressing during the process. So basically, bridge could be a future application, not immediate applications, not gonna push the implementation before we finalize everything and test and verify. As I mentioned, the second project is actually tends itself to be a rocking columns with reinforcement, so bridge column also can be a candidate. Structure that rely on compression, like arch structures, tunnel, and underpasses. So basically, we did like a smaller mock-up for different arch design and segmental arches. That could be also good for, as I mentioned, tunnel lining, underpasses, box culvert, drainage structures. Underwater, if it's scaled up, you really can have another alternative for caisson, bridge caissons. It can have a lot of application in retaining walls, supporting structures, draining and water infrastructure, especially manhole, culvert, etc. A big application for marine and coastal infrastructure where you can protect from sea rise or hurricane storms using like breakwater units or sea walls, and how to integrate different geometry and designs to enable bigger surface areas and damping of the waves energy. Also in emergency responses where we already rely on a massive evacuation. We are lucky during COVID that we don't have big hurricane that require evacuation and social distancing that could also be solved by 3D printing of lightweight concrete wall system and flooring system that enable sheltering people before and after disasters. That said, I would like to thank all our collaborator and funders, and also C2 Smart and Rutgers University and RIME team on BRP for this presentation. I'm happy to receive any questions, if any. If you have any question after the presentation, please email me. I'm almost done here and looking forward for the questions.
Thank you, Dr. Mantawy. It's a very nice and very interesting topic. And I see two questions from Mikhail, that he said, I think you can check it on the Q&A button at the bottom. He said, I can understand the installation of vertical reinforcement by leaving gap during printing, but how you will install the straps during
the stirrups, the stirrups.
Yes, straps.
So the stirrups actually I was not installed, but using the sprayable polyurethane, we were able to provide similar confinement by iteration on the thickness of the material. So there's a different way for confining the column. Still ongoing research. It still can be placed during printing too, But what we have done here is incorporation of vertical reinforcement with casting and using a spray to spray polarity material that is enabling better a confinement to a level that we tested and verified. So basically, using in different application, like where you have a structure or bridges that has bigger spacing between the spiral or ties, you always need to have jacketing. So it's basically an early on jacketing behavior.
Okay, thanks for answering. And another question is the same, people. How is the layer is bond with the following one, noting that each layer lies upon its own weight without any means of compression?
There is means of compression because what we do is we print, basically you have a pressure at the nozzle to extrude. Second is the layer height contribute to, because we run through a lot of iteration where we maximize bond by changing the layer height and make sure that the material is squeezed against the other one. And also during the heat of hydration process within 6 to 8 hours, the heat generation between the material allow us to break the break line between these layers and better fuse. In fact, in the beams that we did immediate casting, we noticed that there is almost monotonic behavior between the printed and the cast material. I actually have it here because I always look at it. If it's in person, you can see it, but you can see that the cast and printed one is fused really nicely together. So it depends on the process, how you maximize the bond between the layers.
And one other question from the same attendee: any environmental or adverse impact when using within the marine or underwater in short or long term?
Yes, if you are using it as a printed offsite and placing it is very different from printing actively in the water, because you will have a lot of leaching. So basically whatever you have in the mix will be leached during the process. So most of the work we do and the people start working on is try to see how much leaching and wash out you receive that will impact the structure and also impact the marine life. We use this pH and deptability test to quantify it, and I think our material is doing well compared to the standard for water. And remember, what we did is in a limited water tank, so the concentration will be different from an open sea and open ocean.
Thank you for answering. And anyone else has any questions? You can raise your hand if you want to ask direct in person. If not, I have some personal question also for your presentation. I noticed that there is a one large 3D printing application in Netherlands in the first couple of slides you show that. I think
Yeah.
that's only for pedestrian. Is there any bridge
Yes,
that
was the Dresden Bridge, yeah.
any built any element, I mean actual structure elements that the vehicle loading can be applied?
Basically, as of now, I know there is some attempts to 3D print concrete. The most 3D printed concrete I saw basically was a printed element that is post-tension together. So equivalent of like, instead of precasting, you're actually segmenting it, post-tensioning it. There is bridge in India that was developed, few in Europe. The technology is evolving and yet to be implemented in highway bridges.
Okay. I think there is something that related to ferro cement, so I think similar, not same technology because 3D printing is printing structure itself, but ferro cement is different. But I think there is some, good combination between having the ferro cement concept, having like meshes with this 3D printing to make
Yeah,
it more improved structure.
100%. Yeah.
Yeah. And one other question that I have, if no one else has, is that I know that you show some strain images with work with Lehigh University.
Yeah.
Just wondering how you can present the strain on the surface like that. I know that when it's cracked, it is obvious you can see the crack, propagation, but I saw like, the strain all across the whole
Okay,
section.
so what we let me go to the slide where I think you're referring to, right?
The one that I think it was, I think, honeycomb structure.
Yeah, so I have some difficulty with my slide, but I think I got your point. Let me reshare quickly. So basically, we are using digital image correlation. We have the equipment here at Rowan where you basically speckle pattern the beam in with different speckles, and there is a high-speed camera that goes and track those speckles, and there's software that's used to convert the movement of those speckles to
Okay.
strains.
But you are sharing the
I think there is something
power.
with the presentation being like 5 GB. Yeah, I let me if you are gonna just reconnect. Okay, I'm sharing my screen now for you to see it.
Mhm. Yeah, you're sharing
So
your screen.
basically this one, right?
Yes, correct.
Yeah, so basically what we have done is we have this the digital image correlation equipment that we spray the surface and we create like a random speckle pattern that with cameras you can correlate those movement between the speckle pattern. It's only surface measurement, so it shows you the strain on the right side,
Hmm.
principal strain as you load the structures. So basically, when the crack form, you lose those patterns. So there is no like the gray lines here, but
Hmm.
outside of that, you can start seeing the evolving strains using the high-speed camera.
Let's see. And okay, just one last question since we still have some time. I think 3D printing materials are very unique compared to conventional material. Is there any like typical procedure to convert from typical material that we develop already to 3D printing, or it has to be from
Yes.
scratch?
Basically, the biggest function of it is how big hoses and nozzles are because those eliminates some aggregate size. Basically, you are using same principle of packing, particle packing, but basically you're using different admixtures to make it more viscous than flowable. Because regular concrete rely on slumping, while this material is relying really on being able to hold its weight and weight of sequential layers. So I have a slide early on that I showed the process here, but I can show it quickly. Where you use flow tables similar to what you have in ultra high performance and setting times, and you're really using the equipment extensively to verify the extrusion and build up. This is our approach. There is also other approaches using reherometers and other like techniques to quantify, but we are doing performance based always in our cases. So this material was developed like 2 years ago, and we use it on all our material. Our compressive strength in casting is around 9 to 10 KSI. As printed, will go a little bit less because of the anisotropy
Mhm.
introduced, so it goes to 7 to 8. With steel fibers, can be even much higher. So you can see here a cross section of fused layer on the left side, and also it's a totally different way of designing, but you have limitation based on the equipment that you are using,
Okay, thank you
especially
very much.
particle size.
Okay, we still have a couple more minutes to audience to ask questions. Okay, I don't see anyone asking more questions, so I think we can conclude today's presentation. Thank you, Dr. Islam Mantawi for today.
Thank you.
And Lizzie, you have announcement?
Yeah, I'm going to send the Zoom link in the chat to everybody for the next webinar, which is tentatively scheduled for June 26th. Let me see.
No.
Sorry, June 23rd
Yes.
at noon Eastern time.
Yeah, the topic is about the fusion of structural monitoring, RIME, and the FEM. So the topic is set, but the time is also set. But if any change, we'll let you know. But we will distribute this link it is on the chat. Also, we're gonna send the invitation email to everybody who have involved today and other colleagues in your team. Okay. Thank you very much, everyone, and hope to see you next webinar. And those who need PDH credit, please email me so that I can issue the PDH credit on behalf of Professor Nasib at Rowan University. Thank you, everybody, and have a good day.